All right, tossing coins. Okay, so find the number of outcomes for the experiment. We're tossing 2 coins. Now you could do this by tree diagram. It's just number of outcomes. So you could either do this by tree diagram, or you could just think, well, the first one has a total of 2 ways it could come out. The second one has a total of 2 ways it could come out. This has got to have 4 total. This doesn't show you what they are. It just shows you that that there should be four possible ways at the end. Sometimes that's good to do that first. Then if you make the tree diagram, or you try to list the table, you kind of know if you. It's one way to check that you've done it right if you know what to expect. It says list the sample space. Okay, so you could do this as a tree. I have me at the beginning here, and I've got 2 ways that we could have this first thing turn out. It could either turn out heads or it could turn out tails. And then after the first one, each one of those could lead to 2 possible outcomes on the second toss. And they would look like this. So how do I list that? It's a little easier to list that here than it was with the burger thing because it was so crazy. There's so many of them. This top path would basically be, I'm going to record what would have happened if you're going to end up here at the top. You would have had heads on the first one, heads on the second one. The second one, this one would have gone heads and then tails. This next one would have gone tails and then heads. And the last one would have gone tails and then tails. Are you surprised by this? You look at these 2 middle ones and go, hey, wait a minute, that's 1 heads and 1 tail. Is that really 2 different things, or is that really the same thing? It's a great question. Well, looking back at the counting principles of what we've talked about so far today, there should be 4. I mean, we've got this idea that there should be at least 4 outcomes. Also, think about this just for a second. Go with me on this. Imagine one of the coins was a penny and one of the coins was a dime. Then not only are these 2 things possible, but they would really look different. One where the heads is on the penny, the other one where the heads is on the dime. And that probability, or those number of outcomes, or those different ways things could change and could sort of happen. Those 2 different ways. That doesn't change if we then all of a sudden start talking about 2 pennies or 2 quarters. We're still going to have these 2 outcomes available. So yes, there really is 2 different ways that we could have 1 heads and 1 tails. It could be this way or this way. We do have to count those separately. That kind of thing comes back over and over again throughout this unit. So if you have trouble with that, I guess it's good that you know that now, and we need to take care of that. So come in and ask me or one of your teacher about that. Anyway, there's 4 ways this should turn out, and those are the 4. Find the probability of exactly 1 head. Okay, well now, once you've got the sample space listed, this is really easy. The probability of 1 heads, so I'm just going to write this out, the probability of 1 heads would be, now, remember this is supposed to be a fraction, and the fraction is the number of ways that can happen over the total number of ways there are to flip 2 coins. Total number of ways there are to flip 2 coins is 4. So out of these 4, how many have this going on? Well, 2 of them. It would be this one and this one. So there's 2 ways out of 4, or 1/2 of the time. We should expect to have exactly 1 heads. Find the probability of 2 tails. Probability of 2t. That would have to be this way. That's the only way that can happen. There's 1 way that can happen out of the 4. Find the probability. So see how easy this is once you have the sample space listed? You can just count and put it in the fraction, and life is easy. Find the probability of getting at least 1 tail. All right. What I'm putting in the parentheses here is just kind of the words for what they're saying here. So when I say exactly 1 head, I wrote that way, 1h. You can put words in here too. This is a little bit better for this one because it's at least 1 tail. You could write out the whole words if you wanted to. That's fine. You could say tails greater than or equal to 1. That's fine. At least 1 tails. All right. So of the 4, again, we're always going to have 4 in this experiment on the bottom of all these questions. How many of these have at least 1 tail? Well, this one, and this one. So all 3 of those do. So we have a 3/4 probability of getting at least 1 tail. That counts having 1 tail or having 2. Okay. In a standard deck of cards, what's the probability that blah, 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 that the top card is such and such? Well, some of you might not know what a standard deck of cards looks like, so I put a picture of it here. You can keep coming back to this and pausing and coming back to this if you want to see this. But a standard deck of cards looks like this. There are 4, we call these suits. There are 4 suits, which is the type of icons you see sort of on the cards. And they're called this: clubs, diamonds, hearts, and spades. Those are the suits. Diamonds and hearts are always red. Clubs and spades are always black. This one that has a 1 on it, or it can be considered a 1 in some games, we call ace also, so there's not really a number 1 ever, there's ace. And then, of course, there's jack, queen, king. Sometimes these are referred to as face cards in the problem. You might get a question like, what's the probability of drawing a face card? Like, what's a face card? What's the probability of drawing a heart? Well, hearts are all of these cards. These are all the 5s. Notice how many there are of each card. There's 52 cards total. We have 4 suits. Each suit has 13. We call these ranks. Okay, so we'll come back to that. In the standard deck of cards, what's the probability that... Blah. Okay, before I even read A, B, and C, I know that all three of these answers are going to look like this. Like they're going to have this in common. All 3 of these are about picking one card out of a deck, or the top card out of a deck, and there are 52 possible cards that could have been that top card. So out of 52 cards, what's the probability the top card is blah, blah, blah? It's going to look like this. Something like the number of ways that card could be a black ace out of 52. So the probability of black, I'm writing black in red, that's kind of weird. All right, probability of black and being an ace. Well, how many black aces are there in the deck? Well, there's this one and there's this one. So there are 2 cards that are black aces. So 2 out of the 52 could possibly be black aces. I'm a little OCD about reducing fractions, so there we go. All right. Top card is not a black ace. All right, so not that. Well, how many cards out of this deck are not black aces? Well, it's all the 52 cards except this one and this one. So there's exactly 50 cards that are not these 2 cards. So notice how when I look at these 2 fractions, those 2 fractions have to add up to 1. If you think about that, that's always going to happen. Probability that something is something or it's not something, those kind of have to total up to 100%, don't they? Okay, top card is a diamond, or is a diamond face card. Probability of a diamond face card. Well, how many diamond face cards are there in the deck? Diamond face cards are, okay, so the diamonds are these, the face cards are these 3. So we're just talking about these 3 cards at the end here. These 3 cards out of the 52. So 3 out of 52, which does not reduce, actually. So we're going to stay there. Okay. There's your one last look at the card deck. All right. 2 dice are thrown. 1 red and 1 green. How many outcomes are possible? Okay. Well, first of all, we know how many outcomes there should be, or there's a way that we talked about to figure out just how many outcomes. The how many outcomes question is related to, but sometimes easier to get at than the what's the list of all the outcomes? What is the sample space? Just how big is the sample space? Sometimes is easier to do first. All right. So how many outcomes should there be? We're throwing a red die and a green die, and they are 1 through 6 sided. So the red one could turn out 6 ways. The green one can turn out 6 ways. So there should be 36 in this sample space. Then it says represent that sample space using a 2-dimensional grid. So the way that works is, because we could do this with a tree diagram, I could start by saying, okay, the first die could turn out 6 ways, 4, 5, 6, and then for each one of those, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, I could do that, and I'd have a list of 36 things. That's one way to do this. That's kind of a mess on this one because it would be so big so fast. So what they want you to do here is do a 2x2 grid. And they kind of want you to do this way. One possible outcome is that, actually let me explain what I'm doing first. One possible outcome we could have on this is both the dice could have 1 on it. So I'm going to do red, comma, green. I'm not going to change my colors because that would take forever. Both dice could be 1. Or if the first die is 1, the second one could then be a 2. Or the first, so this is kind of like that first branch of the tree diagram, where they're all, the ends of the branches where the first die is 1, and then these are all the branches for the second die being whatever it could be. So there's one way to list that, or there's 6 of the outcomes. But that was all just based on the fact that the first die was 1. What if the first die was 2? Well, the first die being 2 could have turned out all these same ways also. Okay. By this point, you might be thinking, oh, wait a second. What's going on here? How come we have those? Is that a problem? Is that okay? Well, remember the thing we had with the dice not too long ago. Just a second ago, we had this dice thing, and we had the 2 here. We're like, what is that? Nope, those are actually different. there are two ways we could get a heads and a tail. It could be the first coin that's the head, or it could be the dime, essentially. Same kind of issue. That's equivalent to this question now here. We're talking about, could the red one be 1 and the green one be 2? Or, you know what, it could have been the red one was 2 and the green one was 1. Those are different outcomes because they're different numbers of colors, actually. Can you tell how this would be filled out if I kept going? I'd put the, whoops, not 5, 6. 5, 1, 6, 1, and I would list 3, 2, down, 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 down to 3, 6, and this would go over to 6, 2, down, 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 down to 6, 6, and I would have this huge grid. And guess how many things would be in this grid? Well, someone else did this, and it looked a lot nicer, and I just copied it from the internet, and it looks like that. So this looks a lot more like what we were just talking about, and notice, yeah, they list this, and this is on purpose, that there's the 1, 2, and the 2, 1. Sorry, that was not the way I wanted that to turn out. Those two are the same. You might think that one and that one are the same, or this one and this one are the same. There's a lot of those on here where they're just the numbers are reversed on the other dice. Those are different outcomes. And notice, yes, there are 36 in here. Oh yeah, this came off when I kept erasing everything. We expected there to be 36 in this list, and lo and behold, there actually are. I'm going to leave this up too. You don't want to pause this or write this down somewhere, because the 2 dice problem, this is the sample space, this diagram or this picture in your head will be very useful when you go back to count stuff that might be favorable, which you'll see here just in a second. So I put a little picture of it up there for these questions. Find the probability that a double was thrown. Okay, so where are the doubles? Doubles would include that. Whoops, didn't mean to cross that off. I thought I had my highlighter. Double 1s, double 2s, double 3s, double 4s, double 5s, double 6s. So maybe it doesn't surprise you, but there are 6 ways to throw doubles out of a total sample space size of 36. Oh, by the way, I know at the beginning of this problem, I can fill all these out like this because I know all these are out of that same sample space. Now, what's the probability that the total of the 2 dice is 10, at least 10. All right, so you look in this and you go, okay, where are the ones that are at least 10? I'm talking about the sum. That looks like it's at least 10. If I just count around, I think those are the places on here where the sums are at least 10. If you look at the way this diagram is constructed, it's actually very helpful. If you look at the diagonals that go this way along here, these are all the same sum. So this is the diagonal where they're all 7. This is the diagonal where they're all 8, and it goes on up to 12. So we wanted the one. Oh, great! I'm gonna have to erase that again. We wanted. Whoops. That 36 is gonna come off. We wanted the ones where it's 10, 11, or 12, and that's just this corner down here. Everything else is going to be 9 or less. So how many are in there? How many outcome boxes do we have? It looks like we have 6. So there's 6 out of 36 ways. Oh, wait, sorry. Let's get away from me. You can leave it as 6 out of 36. This is one of those weird times in math where actually this kind of gives a little more information than this does. Yeah, 1/6 of the time we expect to get a double. Yeah, great. But this actually shows, before we reduce it, we actually see that there are 6 ways to do that out of 36. That actually communicates some information that gets lost when you do this. But you get laughed at math parties if you say 6 out of 36. So 1 out of 6 is better. Find the probability that the total on the dice was less than 10. Well, if there were 6 out here that were 10 or greater, guess how many are less than 10? It would be all of the rest of them. So it's all the rest of them except for those 6. So it's going to be 30. You could count them up, but I don't want to waste your time. Oh man, 1 minute. Find the probability that a 6 was thrown. That a 6 was thrown. Okay, so that's all of these, and that's all of these. Be careful not to count this one twice, because it does only happen. It's only one occurrence, even though it's in both lists. So that's actually, if you count those up, that's 11 out of the 36 can happen that way. All right, now we're on to our last panel. All right, a coin is tossed 3 times. Sketch a tree diagram. I'm going to do that on my own, and you can look. Okay, so I drew a branch with 2 possibilities on each of it for each one of the stages, and then I just wrote the final version of each one up here. So this path that goes, say, this way, tails and then heads and then tails, that's represented over here, tails, heads, tails. So we see the 8. We would expect 8. 2 times 2 times 2 is 8. So the probabilities of these are always going to look like this. Find the probability of exactly 2 heads. Well, if I count those up there, 1, 2, 3. Probability of no tails would only be that one. And the probability of all heads or all tails, if you look closely, will be 2 of those, the top and the bottom of that list. Okay, we'll see you in class.